Hello, everyone, and welcome to this explainer. Today, we're getting into something absolutely massive. We're exploring one of the most profound architectural shifts in modern tech, algorithmic intuition. We're moving way past the absolute basics of machine learning here to really unpack the nuts and bolts of how devices stop just blindly executing our commands and actually start anticipating outcomes. If you follow tech at all, you know this shift is literally everywhere right now. But today, we're popping the hood. We're going to look at exactly how systems make that leap from deterministic programming to probabilistic learning. So let's get right into how machines are bridging the gap to think, well, a little bit more like we do. Okay, let's dive into this. The entire question driving this massive architectural shift is simply this: what happens when we completely abandon hard-coded logic? I mean, for decades, computing was built on this strictly deterministic foundation, right? Engineers write a step-by-step rulebook, and the computer just executes those instructions perfectly. But what happens when we ditch that traditional rulebook altogether? What actually happens when a system stops waiting for our exact parameters and starts figuring out the rules autonomously? It's a total game changer. It's a massive paradigm shift in problem solving that requires a completely different way to approach both architecture and data processing. To really wrap our heads around this shift, think about the fundamental difference between fixed algorithms and learning algorithms. Like we said, for decades, computing was rigid. We wrote clear, sequential instructions. We were essentially telling the machine, do this and then do this. But machine learning? It flips that entire paradigm right on its head. Instead of handing over the rules, we hand over the data, and we tell the computer, hey, figure it out. The system observes, it analyzes, and it draws its own statistical connections. It's developing internal logic based entirely on the information it ingests, rather than just blindly following a predefined path. Let's move to and see how this builds. Because how does this pattern recognition actually function mechanically? Well, it relies on a continuous optimization function. It's this core feedback loop of guess, check, and improve. And it's absolutely crucial to understand that this isn't some linear start-to-finish process. No, it's an ongoing cycle that serves as the literal heartbeat of algorithmic intuition. The model is constantly engaged in this loop, using probabilistic outcomes to iteratively refine its accuracy over time. So let's break down the foundational steps of this continuous feedback mechanism. Here's how that optimization loop actually plays out. Step 1, the model ingests training data. Step 2, it maps that data, tries to find a pattern, and generates a probabilistic guess. Step 3 is the validation phase, where we check the guess and provide right or wrong feedback. And finally, step 4, the model improves by adjusting its internal weights to reduce the margin of error for the next time. So it's ingest data, generate a prediction, validate the work, adjust the weights. Over and over. It's basically a highly efficient algorithmic version of trial and error that's constantly minimizing its own loss function. Let's ground this a bit with visual feature extraction. When we talk about feeding a model thousands of explicitly labeled dog and not dog images, you've got to remember the system isn't just looking at pictures the way you or I do. It's mapping a really complex latent space. It is extracting these minute visual features. We're talking the specific pixel gradient of a curved ear or the exact geometric ratio of a snout. These are parameters that a human programmer could literally never manually code with absolute certainty. The model uses this vast dataset to mathematically map the highly specific variances that separate the target from the noise. And ultimately, because the system has completed so many of those validation cycles and adjusted its internal weight so precisely, it achieves the absolute holy grail of machine learning: generalization. As the saying goes, eventually it gets very good at spotting dogs, even ones it's never seen before. And that's the magic, right? The model no longer needs to have processed a specific image to accurately classify it. It has learned the underlying statistical essence of the target subject. It can successfully infer outcomes on entirely novel, unseen datasets. And this brilliantly illustrates how this capability for generalization powers the seamless tech experiences we use every single day. Think about it: Netflix recommendations, Siri and Alexa, adaptive video game AI, and of course, email spam filters. What's truly staggering here is the sheer scale at which these systems operate. Modern voice assistants are using hundreds of millions of parameters to parse your specific accent in real time. And that recommendation engine on your streaming app? It's estimated to save the company over $1 billion a year simply in reduced subscriber churn. And it's all driven by that relentless feedback loop working quietly in the background. Let's focus on that last example for a second, the spam filter, because it perfectly captures this impact. Years ago, our inboxes were a chaotic mess. We all remember manually deleting endless emails from Nigerian princes or, dubious lottery winners. It was a massive chore. But today, we enjoy a beautifully clean inbox with the spam just seamlessly routed away. This wasn't achieved by some poor programmer sitting down and trying to manually hard-code every single permutation of a scam email. No way. It was achieved by feeding the system massive data sets and letting it extract the features completely on its own. Now, what's really interesting about all this is how this system accomplished it through advanced feature extraction. By running millions of good and bad emails through its optimization loop, the model learned to spot anomalies. It doesn't simply read exclamation points or trigger words the way we do. It assigns statistical weights to anomalies in punctuation, syntax, and specific vocabulary. It mathematically weighs the probability that a certain cluster of words and symbols indicates a bad email, refining its internal boundaries with every single message it processes. We know machine learning excels at extracting these complex features, right? Whether it's the pixel geometry of a dog's ear or the weighted syntax in a spam email. But identifying a pattern is really only half the battle. So the crucial point is, how does it cross the threshold from recognizing a statistical anomaly to definitively classifying an email as spam? That requires complex decision boundaries and branching pathways. How exactly does an AI model make that final judgment? Well, that's the perfect question to leave you with. You'll have to join us next time as we unpack the architecture of decision trees and the actual math behind those final choices.